Greetings and welcome to Lecture 3.3, Graphing Linear Equations in Two Variables. So in the last lecture we started talking about solving linear equations in two variables, but actually we were only finding a couple of solutions. And as before, when we have a combination of two variables, we actually have infinite many possible solutions. And because of that, we can visualize all of our solutions by graphing it. So let's go back and just remember how to graph an ordered pair. So let's take a look at some of these ordered pairs. A is 0, 3. So I didn't move left or right any, but I did go up 3. So A is 1, 3. B is -2, 4. So I'm going to be -2 down 4. There's my B. C is -5, 1. So on the X, I go to the left -5, but I go up 1. D is 4, -2. So I start at the origin always, move over 4 and down 2, and there's my D. My E is -2, 0. I go to the left 2, but I don't go up and down any, so I stay on the axis, the x-axis. F is 4, 0. I don't go left or right any, but I do go up 4, so I stay on the y-axis. G is 4, 2, so I move to the right 4 and up 2. And H is 0, -2. So again, no lefting and righting, but I do go down 2. So that's, if you recall, graphing an ordered pair. Now, graphing linear equations with two variables, what we do there is we have our equation and we pick some points. Doesn't necessarily have to be specific points for x. That's usually where we start off, is x. And given some values of x, I'm going to find out what y is. And I'll find the coordinating point. So if x is 0, plug in 0, y will be 5. When x is 2, y is 3. When x is -1, y is 6. I go ahead and plot those points, and then I draw a line through all 3 points. That line signifies all of the solutions to x plus y equals 5. Here's what I mean. Now I'm picking something that wasn't in our table. So let's say I say -1. If I go up to the line, I get to 6. My y is 6. -1, 6 is a solution, right? And then, and I plotted the wrong one. There we go. -1, 6. What I mean is, if I go over to 6 and down to the line, that's a solution. If I go over, let's say 1 and up to the line, that's a solution. If I go 1.5, get up to the line, that's a solution. Every single point on this line is a solution. And it'd be impossible for me to do little itty-bitty dots everywhere, so that's why we connect the dots and create a line. Now there's a couple of ways that we can write a linear equation. The first format is the linear equation in standard form. So any equation that can be put in the form of ax plus by equals c, where a, b, and c are real numbers, and a and b are not both the zeros, is called a linear equation in two variables. And it looks like ax plus by equals c. That's called the standard form. So to graph a linear equation in two variables, step 1 is to find any 3 ordered pairs that satisfy the equation. That means you pick an x, you solve for y, or you pick a y and you solve for that corresponding x. And you do that 3 times. Why 3? Because 2 points, when you draw a line, you'll get the line. but the third point will check to verify that you are indeed on the line. So 3 points. Graph the ordered pairs. Okay. Again, we need 2 points. With 1 point you can't draw a line. 2 points you can draw a line, but the third is a check. And then you draw a straight line through the plotted points. And I do mean through the plotted points, not just connecting them. A line goes through those 2 points and out to infinity. So let's graph the equation y equals 3x minus 1. So in standard form, I'm going to rewrite it in standard form by moving the x over. Remember, ax plus by equals c is called standard form. To graph it, that's not necessary, but I want to show you what it is in standard form. Negative 3x plus y equals 1. I pick a few numbers, 2, 0, negative 2. That's pretty good. I plug them in for x, so y equals, and I went ahead and I'm using the original equation to do my math. I just wrote it in standard form. So 3 times 2 minus 1 is 6 minus 1, which is 5. So the corresponding point for y is 5 for 2. Let's try 0. 3 times 0 is 0. Minus 1 is negative 1. Let's try negative 2. 3 times negative 2 is negative 6. Minus 1 more is negative 7. Now, I plot those points. Okay. Here's 2, 5. Here's 0, negative 1. And 2, negative 2, negative 7. Get out my little ruler. Connect the dots, go through those dots, add the arrows, and now I have found every single solution of that formula, or of that function. Pardon. So I've completed another example, but I want to walk through this problem still. So I want to graph y equals negative 1/3 x minus 2. Now you might be saying, ugh, fractions. But don't worry about the fractions. We can easily get rid of the fractions. What's the denominator of the fraction? 3. So if I choose my x's carefully, as in 3, 0, and negative 3, I can eliminate my fraction. So choose wisely the numbers that you do select for x. Negative 3 times 3 is negative 1, plus 2 is 1. See how easy it is with fractions? Let's get rid of them. And 0 will always get rid of a fraction if we have a fraction times x. So 0 times negative 1/3 is 0, plus 2 is 2. And negative 3, that's just the cleverest way of doing a negative 1/3 times a negative 3 will give us a positive 1. Remember, we don't like fractions to work with them, so let's get rid of them. Plus 2, so 1 plus 2 is 3. Plot the points. Connect the dots, add your arrows, and you have all of your solutions to y equals negative 1/3 x plus 2. Now that's nice that it was already done for us, but let's try one all to ourselves, right? So the numbers that I generally like to work with when I'm selecting an x is simply 1, 0, and negative 1. Those are always nice numbers to work with generally if I don't have any fractions. Numbers don't get too large, they don't get too weird, so I do try to do 1, 0, negative 1. I do want to add a little bit of information to my graph just to make sure that you know what I'm counting by. Just enough. 5, 6, and my negatives. Otherwise, I could count by 2s. I could count by 3s. I'm only going to count by 1s. Or each index could be more than just a 1. It could be 2, 3, 4, whatever. So I'm going to go ahead and label my graph so you recognize what the unit count will be. So now let's work out some of the problems. 3 times 1 minus 2y equals 6. I have 3 minus 2y equals 6. 2y minus 3, negative 2y equals negative 3. So my solution is y is 3/2. Don't worry about that. 3/2 is just fine. Let's use 0. I'm just going to do it off to the side here. 3 times 0 minus 2y equals 6. 0 minus 2y equals 6, so y equals negative 3. That's a little bit easier to plot, at least. And let's try when x is negative 1. So negative 1 minus 3 times negative 1 minus 2y equals 6. Negative 3 minus 2y equals 6. Add 3 to each side, negative 2y equals 9. So y equals negative 9/2. Again, don't fret about that fraction. Okay, so let's start plotting this. I'm going to take the easiest one first. Let's do 0, negative 3. So 0, negative 3. 0, negative 3. All right, we got 1 taken care of. Let's try 1 3/2. So I move over 1, and 3/2 is another way of saying 1 1/2. So I'm going to go up 1 and a half more. So I am 1, 3/2. Just because I don't have it on the label, it does exist. I just have to guesstimate where the half marker is. And negative 1, negative 9/2. Well, negative 9/2 is 4 1/2, so I'm going to go 1 and 4 1/2 more. So if my graph was pretty good here, and it's a little bit off, but that's because I'm not very accurate, I'm going to do the best that I can at connecting my dots. And you see I'm off a little bit, but it's actually a good thing that I did this, because here I'm trying to connect my dots and it turns out I have an error. Right up here, this should not be a negative 3, that should be a positive 3, so my solution is a negative 3/2, hence the 3 dots. If I didn't have 3 points, I wouldn't recognize my error. So if I plot this real point, it's 1 and a negative 1/2. Look at that, my dots do connect. And if that ever happens to you, either get some white out, or that is 1, negative 3/2, or just, signify that it was wrong. But I'm really glad that I actually had that error for a change, and that I could show you that having the 3 points really makes a difference. That's the end of part 1 of this lecture, so until part 2, be seeing you.